Hello, this is Timberlake Basic Chemistry, and we're in Chapter 8 on chemical reactions. This is the second lecture of Section 8.1 on equations for chemical reactions. So today we're going to learn how to balance chemical equations, and we need to start simple because it is a little more involved. We're going to look right now of balancing the matter on both sides of a chemical reaction. So we start with reactants, and reactants are anything that will react together, and then you have an arrow which indicates a yield sign. So this is production of something. So we're taking one or more reactants, let's say some kind of a compound A and B, and we're making them into products. So you're producing something, and this could be C or C plus D or any combination like that. So to the left is reactants coming together to make something. To the right is products being made into something. And our task today is to realize that these reactants each are made of components. So unless A or B is an element, compounds are made of more than one element and a combination of more than one element. So for instance, water is H2O. There's two hydrogen atoms and one oxygen atom combined chemically to make a water molecule. So if A in this case were water, before you can make C and D, everything has to disassemble. So you're breaking the hydrogen and oxygens all apart, and then whatever the B part is are reconfiguring into some new product. So today's idea is that the same amount of matter, same amount, is on both sides of a chemical reaction. You cannot produce matter or get rid of matter simply by doing a chemical reaction. The same amount of stuff is at the beginning and the end. You simply take it all apart, all of the bonds break between the old molecules, and new bonds form within the products. So in a chemical change, remember you have something new. So silver tarnish has different properties than silver metal. And it is now a compound of silver plus, in this case, sulfur, and that's not the same as sulfur, and it's not the same as silver. They look different, and all of their properties are different. So a chemical reaction, if you'll remember that we've talked about this before, you can tell that a chemical reaction's occurred with a temperature change. It's either gotten hot or cold, because that's the second part that we're not going to look at today, and that's that energy is changing. It's not just that matter is changing from one side to the other of a reaction, but there's energy either being lost or gained as a reaction occurs. And so the temperature change is one indication. Another would be a color change. So this silver fork is now black and cruddy. That change in color has indicated that there's actually been a chemical change to the surface metal of that silver. Others would be, for instance, in a liquid situation or aqueous where there's bubbles produced, where there's a gas produced. That's another indicator. And there are more, but those are the kind of obvious ones. So in a chemical reaction, the chemical change produces one or more new substances. So the properties of your reactants and the properties of your products are different. You may have a color change, you may have a temperature change, you may have a gas production, you may have differences in viscosity or distance in boiling point or differences in a number of things as one thing becomes something else. What's in the back of your mind is that those molecules that break apart and new molecules form are themselves made up of elements. So think of that as a big box of Legos, and if you're going to make one thing, you have to take apart what you made before. So you take apart all the Legos and then you put them together in a new configuration. So today we're balancing equations. We want to make sure that the same amount of matter exists on both sides, left and right. And it's not always apparent, because if I say water reacts with or in this case, hydrogen reacts with oxygen to give you water. Well, how much oxygen am I going to need? And how much hydrogen am I going to need? And how much water will I make? It just saying water and hydrogen and oxygen is not enough. You're going to have to make sure that at the end of that equation, it's truly equal. And what we're talking, equation comes from word equal. What's equal here is the matter, the same amount of atoms on both sides. So if you think of this as 2 reds and 4 whites, on the left side you've got 2 reds and 4 whites. On the right side you have 2 reds and 4 whites. Okay, and so you have to configure it back and forth until you have equal numbers on both sides. That's the lowest ratio that you can get to. Okay, so you can't say 8 whites and 4 reds, because that's just doubled amount. You have to put it down to the smallest ratio to where those atoms will combine to make the new things. Okay, so the reactions are on the left, the products are on the right. The number of reactant atoms is the same as the number of product atoms. You're not going to gain atoms by doing a chemical reaction, and you're not going to lose them. All right, so here's the first one. We've got phosphorus plus 6 bromine molecules yields phosphorus tribromide. Okay, and I need to make sure the same amount of atoms are on both sides. So I'll look over here to the first part, and I've got P4. Okay, that means that I need P4 on this side. Well, do I have P4 on this side? I've got a coefficient here, which is saying I have 4 of these molecules. How many phosphoruses do I have if I have 4 of those molecules? Okay, so here I have 4 phosphorus and 4 phosphorus. So that's great. That means that those are balanced. All right. What about the bromine? I've got 2 bromine atoms in one molecule. I've got 6 molecules. That means I have 12 bromine atoms on this side. Do I have 12 on the other? Well, I've got 3 in each molecule, and I have 4 molecules. So 4 times 3 is 12. I have 12 bromines. And yes, my bromines are the same, and my phosphoruses are the same. So that is balanced. A is balanced. What about 2? Okay, I've got 2 aluminums because I have 1 aluminum atom, but I have 2 atoms. 2 atoms of aluminum. What about on the other side? Well, this is in a compound, but how many aluminums are on that side? I have 1 molecule with Al2 in it. So this is 2 aluminums. This is 2 aluminums. So my aluminum is fine. Okay. What about my iron? This is embedded inside a molecule. I've got 2 of them. What about here? This is not in a molecule. That's 2 iron atoms. So I've got 2 atoms. And then I've got this. So embedded in subscripts. Okay. When it's not embedded in, you have coefficients. A coefficient just means I have 2 of them. I have 2 of the irons. So I have 2 irons on the left, and I have 2 irons on the right. My irons are balanced. Okay, what about my oxygen? I've got an O3 on this side, and I only have 1 molecule, so that means I have 3 oxygens on the left, and I also have 3 oxygens on the right. So that is a balanced equation. Okay. To write a balanced chemical equation, there is the same number of each type of atom in the reactants and the products. Okay, so the number that multiplies in front, say 1 aluminum or 2 aluminum or 1 sulfur or 3 sulfur, are called coefficients, and it simply multiplies by that molecule. So the number of atoms in each molecule would multiply by the coefficient. The coefficient sits in front. So here, this is the coefficient of 2. It's showing you that you have 2 aluminums. This is 3, it's showing you have 3 sulfurs. In this case, that is how you do aluminum sulfide. Aluminum is positive 3, since it's in group 3. Sulfur is negative 2, since it's in group 6. And so this negative 2 and this positive 3, remember, does the switch, and the 3 becomes the subscript of the sulfur, the 2 becomes the subscript of the aluminum. Well, this is still 2 aluminums. So 2 aluminums and 2 aluminums are the same. That's a balanced aluminum. 3 sulfurs and 3 sulfurs are balanced. So in order to take sulfur and make it the same as something that's S3, I have to have 3 of them. I have to have 3 atoms in order to make something that has 3 atoms of sulfur embedded inside a formula. Okay, try this one. Sodium plus nitrogen gas yields sodium trinitride, or sodium nitride, sorry, sodium nitride. Well, I start on the left. My rule of thumb is that oxygen and hydrogen last. I do everything else first, okay? And I'll do oxygens and hydrogens last. So I just start over here since it's the left. I've got 1 sodium. I look on the other side, I have 1 sodium. Great, my sodiums are fine, okay? I come over here, I've got 2 nitrogens because nitrogen gas is diatomic, means it's always going to be 2. H2, N2, O2, and then the group 7, chlorine, fluorine, chlorine, bromine, iodine are diatomic. So this is N2. But over here I have a 3. So I have 2 on the left and 3 on the right. Well, in order to make them balanced, I need a multiple of 2 and 3. Okay? Well, so I'm going to take a coefficient because I can't change the subscripts at all because the subscripts are based upon that molecule. I can't change the subscript. That's the recipe, that's the formula for that molecule, but I can multiply it by a coefficient. So 3 times 2 is 6. So I have 6 nitrogens. And then in this case, I have 2 times 3 is 6, and I have 6 nitrogens. So my nitrogens are balanced too. So you fix the inequity on both sides by multiplying one or more by numbers to make them both equal. But you will need to make the smallest multiple. The lowest common multiple is what you want. The LCM from 6th grade, if you remember that. All right, let's look here. Remember, I'm going to do oxygens and hydrogens last in B. So let's start with carbons. I've got C2 and C2. So carbon is fine. Okay. Now let's look at oxygen. Over here I've got 1 oxygen, and over here I've got 1 oxygen. So that's 1 to 1. So right now oxygen is also balanced. What about hydrogen? I've got 2 on the left, I've got 1 on the right. So to fix it, I have to multiply the whole thing by 2. Okay, which fixes my hydrogens. My hydrogens now have 2 and 2, but I've messed up my carbon and I've messed up my oxygen. I have to redo them. So things you've already done, you have to redo. So I'm going to go back, and now I have 2 times 2. 2 times 2 is 4. So I have 4 carbons, and now I need 4 carbons on the left. Well, I've got 2 is embedded, so I have to multiply the whole thing by 2. So I have 4 carbons. So carbons are fine. All right. Now, what has that happened to the hydrogen? I've got 2 times 4, that's 8. Okay. Plus 2 more. Okay. Oops, I made a mistake. I do oxygens, then I do hydrogens last. So let's fix the oxygens first. So I've got the carbons 4 by 4. And now I've got 2 times oxygen, so I have 2 oxygens. And now I need 2 oxygens here. I've got 1 oxygen, so I need 2 oxygens there. So now I have 2 oxygens. Now I'll do hydrogen last. Okay. Well, how many do I have on the left? I've got 2 times 4, so that's 8, plus 2 times 2 is 4. Okay. So 8 plus 4 is 12. I have 12 hydrogens. Okay, how many do I have on the other side? I've got 5 and 6. 5 and 1 are 6, and I have 2 of them, so that's 12. So my hydrogens are balanced, my oxygens are balanced, and my carbons are balanced. Okay, that's how you do it.